Welcome to Brain Bites. In today's explainer, we'll explore a topic that directly influences our health, daily habits, and overall well-being, often in ways we may not even notice. Let's uncover the facts and understand how these everyday choices can shape our lives. Okay, let's just dive right in. The unseen system we're talking about today is literally the foundation of modern human existence. I'm talking about the most complicated, absolutely massive machine humanity has ever built, and somehow it's just hiding in plain sight. It's the electrical grid. And just to give you a sense of the sheer, unfathomable scale of this invisible machine, if you were to take all the transmission cables across the world and string them out end to end, they would stretch 42 million miles. I mean, think about it. That is almost halfway to the sun. Insane, right? But despite its massive size, this entire grid is currently undergoing a complete radical transformation right beneath our feet. Part 1. The AI energy shock. So, for like the last 20 years, wealthy Western countries really haven't had to think about their grids. Why? Well, because electricity demand was basically entirely flat. But this recent stagnation sharply contrasts with our history. Back in 1910, just 14% of US homes had electricity. Then, in just 2 decades, by 1930, that rocketed all the way up to 70%. It was this era of explosive economic growth, and the grid expanded right alongside it. It seemed pretty much unstoppable. But that nonstop expansion eventually hit a brick wall in the 1970s. The oil crisis struck, energy got super expensive, and our entire focus shifted dramatically toward efficiency. And this pivot is actually brilliantly illustrated by the New York power company, Con Edison. They literally changed their iconic company slogan from "Dig we must," which, implies this endless building, to "Save a watt." Combined with our economy shifting away from heavy manufacturing and more toward office work, electricity demand in the West effectively just flattened out. And that brings us to today's massive interruption. That long, quiet era of flat energy use, it is totally over. We are currently experiencing a massive, sudden demand shock, and it's being driven by 3 heavy hitters. Millions of new electric vehicles hitting the roads, people adopting heat pumps to replace old gas boilers, and a staggering $300 billion artificial intelligence boom. Because of these incredibly power-hungry AI data centers, global electricity use is predicted to literally double by 2050. To put that into perspective, that's essentially adding a whole new USA's worth of electricity to the grid every 5 years. And honestly, this isn't just an infrastructure headache, there are intense geopolitical stakes here. Just look at this comparison. While Western economies essentially let their grid supply chains atrophy during those decades of flat demand, China's grid expansion has been going nonstop. Actually, power generation in China has increased 7-fold since the year 2000. It's a stark reminder that the battle to build the best grid is essentially the battle to win the future. Which brings us to part 2, supercharging power lines. So we have this massive physical hardware problem, right? How do we actually move all this new power? We physically cannot keep building traditional transmission lines fast enough. Enter innovative tech companies like Veer. They are attempting to completely rewrite the rules of transmission cables using superconducting materials. Now, most traditional cables, like your standard copper or aluminum, have resistance, and resistance means energy gets lost as heat while it's traveling. But a superconductor, under very specific conditions, has absolute zero electrical resistance. None. This means a single, incredibly compact cable can carry exponentially more power than traditional wires. Game changer, right? Well, there is a huge catch. To reach that magical zero-resistance superconducting state, these materials have to be kept incredibly cold. We're talking 77 Kelvin. Veris actually achieves this by pumping liquid nitrogen straight through the cables. Just to give you an idea of how cold that is, 77 Kelvin is roughly the temperature of the dark side of the moon. So it is a massive, massive physics challenge to commercialize this tech across hundreds of miles of open terrain. If you're finding this explainer helpful and informative, we'd appreciate your support. A quick like on the explainer helps the channel reach more people and enables us to continue creating valuable content for viewers like you. Now, even if we do manage to build these incredible frozen cables to carry the electricity, we face an even bigger, much scarier physics problem. Can we keep the grid stable? Part 3. The inertia problem. To really understand what happens when grid physics fail, we have to look at the worst blackout in Europe's modern history. Not too long ago, this massive power outage struck Spain and Portugal. Millions of people were left in the dark, folks were literally trapped in trains, and an estimated 400 million euros were just wiped out of the Spanish economy in an instant. You see, the grid requires second-by-second perfect harmony. The electricity being generated must perfectly match the electricity being consumed. When that balance fails, you get this terrifying domino effect. First, a supply imbalance causes unpredictable voltage spikes. Then, parts of the system rapidly disconnect to avoid burning out, and suddenly the entire grid collapses. Fortunately for us, the traditional grid has a built-in saving grace, and it's rooted directly in high school physics, Isaac Newton's first law of motion, inertia. Think about traditional coal, gas, or nuclear plants. Inside them, you have these massive 100-ton metal turbines that are physically spinning. If a power plant suddenly drops offline, those massive metal components actually keep spinning for a moment simply due to their sheer physical momentum. That physical inertia acts like a kinetic buffer, naturally injecting just enough power to keep the grid stable for a few critical seconds so operators can react. But here is the fatal flaw that caused that Spanish blackout. Solar panels convert light directly into electricity. Because there are no massive spinning generators involved, there is absolutely zero inertia. So as Spain rapidly added all this cheap, clean solar power to their grid and started retiring their older power plants, they unknowingly stripped their entire grid of its physical spinning mass. When a solar plant dropped offline, there was zero inertia left to catch the fall. The solution to this is honestly absolutely fascinating. European power companies are now installing these things called synchronous compensators. They are essentially giant, 100-ton spinning metal cogs. They just sit there in a building, rotating at 1,500 RPM, and they generate absolutely no electricity. Their sole purpose in life is just to spin really heavily, providing that crucial physical inertia back to the grid, but without having to burn a single drop of fossil fuels. It's brilliant.
All right, part 4. Africa's mini-grid revolution.
While Western countries are spending billions to stabilize these high-tech grids for AI, we really need to pan out and look at the global scale. Because right now, in sub-Saharan Africa, over 565 million people still lack any access to traditional grids whatsoever. But rather than just being left behind, they are actually leapfrogging the traditional model entirely. Private companies like Husk Power, for example, are completely bypassing massive, expensive transmission lines. Instead, they're building localized, solar-powered mini-grids. These are specifically designed to serve small, rural communities of maybe 400 people. It gives them 24/7 power, which completely jumpstarts the local economy. It allows kids to study at night and powers vital equipment like local rice milling machines. And remember, every massive grid has to start somewhere, right? That brings us to Mission 300. It's this incredibly ambitious World Bank-backed project. The goal? Connect 300 million Africans to electricity by the year 2030. And their strategy is to start with these localized mini-grids, and then, over the coming decades, gradually interconnect them until they eventually form a massive, robust national grid. Which leads us to our final section, Part 5, Energy is Destiny. When we step back and look at this explainer as a whole, a really clear picture emerges. Whether you are powering a $300 billion AI data center in the United States or a rice milling machine in a rural Nigerian village, electricity infrastructure is the ultimate foundation for all human progress. Ultimately, energy is destiny. A country's ability to innovate, build out, and stabilize its electrical grid won't just determine if their lights stay on, it will directly dictate their economic competitiveness and their prosperity in the 21st century. The machine around us is evolving, and whoever builds it best, well, they win the future. As the global grid physically rebuilt itself right beneath our feet, we really have to ask, is your local grid ready for the shockwaves of the next decade? Thank you for watching. If you enjoyed this explainer and learned something new, please give it a thumbs up, share it with friends and family who may benefit from it, and subscribe to Brain Bites for more engaging, educational, and thought-provoking content.